Okay, we want to look at the undrained strength of clay and silt in more detail here. So remember, we have our EDS tough, and what are we talking about? Well, this was effective drain slow. That's not what we're on. We are on undrained, so we're on total undrained fast. Now, the test has two phases, as we said, the consolidation phase and the shearing phase. And the consolidation phase, it looks like this, where we simply apply a vertical load to consolidate the sample. I'm showing it completely underwater so that the clay stays saturated, but what happens is we consolidate it and the excess pore pressures become zero at the end of the consolidation phase. At the end of the consolidation phase, the excess pore pressures are zero. So in other words, we apply the P and wait 24 hours, for instance, for all the excess pore pressures to dissipate. So therefore, before shearing, the excess pore pressure is zero. And our sigma prime then is equal to sigma, which is simply P over the cross-sectional area. And we call this sigma prime I, the initial effective stress, sigma prime I. I'll be calling it sigma prime I. The shearing phase, what do? Well, we put on the F. So the P remains, it's constant, and we increase the F until we get failure. So we apply the F quickly. So in other words, this is the shearing phase is the quick part, the fast part. So there is no U excess dissipation during the shear loading. So in other words, we generate our excess pore pressures with the shearing stresses that we apply here. And, typical result will look something like this. So in other words, we increase F again until we get failure. And what do we find? We find the excess pore pressure then is generated due to this shearing. So these are both plotted. I have delta. Delta is the amount of deformation of our sample. And so these line up here. So I have delta is the x-axis for both of these, and there is a match between. So these line up here. So when I get an F at the peak, there's my U excess. So that is a typical result for a normally consolidated type clay. So. And just as a little refresher of your memory here, you did a uniaxial tension test in your materials class or some class that you've taken. And what was it? Remember, we had steel, and we loaded the steel in tension, and we got a deformation delta, the original length L, for instance, and then our normal strain was delta over L. And we could plot up our stress strain curve, and it looked like that. Well, when we do a shear test on soil, what's happening here is that we have the top of the box and the bottom of the box, and then we have our shear plane. The shear plane is just in this region, basically, and a plane, we call it a shear plane. And if we look closely at that shear plane, it's separated. We have this little region that is being stressed. And it originally started out as a rectangle, and now it becomes a parallelogram. And we can define the shear strain, again, delta over L. We measure delta and L differently. But here we have delta over L is our normal strain. Here we have delta over L is our shear strain. So just a different definition of strain, but it's very similar. So we can create, again, another stress strain curve. So our tau gamma instead of sigma epsilon, and we get our curve, and it's similar to the sigma epsilon curve. So I want to note that in this particular case, again, so you don't get confused, gamma is the traditional symbol for shear strain, so we use it, gamma. It's not density, so just be careful, because in geotechnical engineering we like to use gamma for density or unit weight, but in this particular case it means shear strain. So okay, so let's look at this example. We have two tests on the same clay. So I'm showing them, we often put them on the same stress strain curves. So both tests are undrained, and we measure UXS during the test. So we have our UXS plot, and again, notice how these all line up. My x-axis for both of them, I'm using gamma, and we have tau on the y-axis here. We have UXS on the y-axis there, and we have 0, and UXS increases going downward, so just be aware of that. And we're saying the soil is normally consolidated, and we want to find C prime and phi prime, and SU over sigma prime I for this clay from these two tests. And that is our goal. And I've given you the sigma prime I here, and that, of course, is the effective stress in the sample at the end of the consolidation phase, which means that it is the sigma prime at the beginning of the shearing phase. And okay, so what we're going to do is we're going to find the peak, and we're on the curve, and get the UXS of that peak. So I'm sort of giving it to you, but notice the way these curves work. This one is at 30 kilopascals, this one's at 30 kilopascals. So in other words, this curve here goes together with that curve there. So we don't want to get confused. We don't want to mix these up. So, and this curve here goes with this curve here. So that one and that one and those two go together. So I'm showing 4 curves, and so once again, this curve and this curve are both from the same test. And this curve and this curve are both from the same test. So, and again, I have shear strain, it's not density. And what we find is that I look for the peak basically here, and I find the UXS that goes with that peak. It's there. So the 22 and 8, these two numbers go together. Well, those 3 numbers go together, the 22, 8, and 30 all go together because that's one test. And then we have our other test. We look for the peak. The peak is there. And then at that strain, I look for the U. So I get that, and that. Those 3 numbers go together. So the 60, 46, and 12. All right, so my goal is to take these test results. So this is the results that you got from a test. And we want to find these soil properties. So how do we do that? Well, first thing we're going to note that there's a little bit of trick going on here, and that is our test is a quick test or fast test. It's undrained. So we are, in a sense, we're doing the tough. Well, that's what we're doing, but There is a trick whereby we can get the drained strength parameters, which are C prime and phi prime. They're drained strength parameters, but we can get them from our undrained test because we measured U excess in the test. So that allows us to get sigma prime. So luckily we measured it. So we can get sigma prime, which means we can plot it on our sigma prime plot. The other part is, in theory, our SU over sigma prime I is constant for a given OCR, for a given clay. So we are going to use this theory. It works pretty well. And we are going to get that ratio. So let's plot up let's put this into a table. And we have our two tests, test 1 and test 2. We had one that had a sigma prime I of 30, the other 60. And remember the numbers when we had 30, 22 for the tau FF. And we had the 60 and 46, the sigma prime and tau, sigma prime and tau. So in other words, let's go back. So I had 30, 22, 60, 46. I put those onto the table. And because this test was fast, what do we find? Our tau FF is what? It's our SU. So we have both 22 and 46 are our SU undrained shear strength. So, and since we have our sigma prime I and we have our SU, or undrained shear strength, then we just simply take the ratio, 22 over 30 and 46 over 60, and we get 0.73 and 0.77. Okay, that's close. It's not exact. In theory, they should be the same, but in reality, they're never exactly the same. So we can simply take these two values and come up with an average, and we get about 0.75. So good enough. We have our U excess for both of these, 8 and 12, and that means we can get our sigma prime FF because we had our initial effective stress and had a U excess of 0, so that was also sigma. And so our sigma prime at failure on the failure plane is simply the 30 minus the 8 to give me 22 for that one. And this one will be 60 minus 12, which is 48. So we can get, because we measured the excess pore pressure, we can get the sigma prime at failure on the failure plane, sigma prime FF. So what we're going to do now is we are going to plot these two columns to get our C prime and phi prime, our sigma prime FF and our tau FF. We've already obtained our SU or sigma prime I. Now we want to get our C prime and phi prime. And just, yeah, so SU, undrained shear strength, is tau FF. And SU is the shear stress at failure. SU undrained shear strength. And sigma prime FF is sigma prime on the failure plane at failure. So let's plot up these two on our Moore diagram. So we plot up our sigma prime and our tau, and these are the numbers. So sigma prime is the x, tau is the y. And so we have what? 22, 22, 48, 46. So there they are, 22, 22, 48, 46. We draw a line through the two of those 2 points, And that is our failure envelope, so meaning that if we're below, it's no failure. If we're above, if our stress in situ is above, then we do have failure. So, and the intercept we call C prime, the angle there we call phi prime. And what we want to do our calculations is that we want to write an equation of that line using y equals mx plus b, and noting that our b, our intercept, is c prime. So we know m is what? The slope. It's a delta y over delta x. So we have our delta y, our delta x. We get 0.92 for the slope for that line. And then using y is equal to mx plus b, 0.92x plus b. We use one of the points. I guess we can use that point. We can use that point also, but for this example, we chose to use that point. So we put in x equals 48, y equals 46 into this expression. We solve for b. We get b equals 1.76, which means that c prime is equal to 1.76 kilopascals. And then we have our slope. The angle is the arctangent of the slope, which we know. So we've been able to find c prime. We've been able to find phi prime. We now have our strength parameters for this result. Okay, so what I want you to do is do the same thing for this. And I've given you a table. You can copy the table down. And I want you to do what we just did. Find the SU over sigma prime I and the C prime and phi prime for these two tests. Here's our cross-sectional area is 0.7. So remember, I just take the F divided by the cross-sectional area to get my sigmas. Or sorry, F over cross-sectional area to get the tau. P over the cross-sectional area to get the sigma. And we have our UXS's here. I've already drawn them for you. So we get the peak, we come down, we get those values. So pause the video, fill out this table, get that started anyway. Okay, I've assumed you've done this. So what do we have? Well, we have, let's start with the P's. We have 1,500 and 4,000. So we have 1,500 over 0.7, the 0.7 being the area. And we have 4,000 over 0.7. So we got our sigma prime I. In other words, that's the end of the consolidation phase. We get the sigma prime I. Then what? We read off our taus. 750 and 1,600. So 750 over 0.7, 1,600 over 0.7. So we get our tau FFs. Our SU, since these are both fast or quick tests, our SU and our taus are the same, tau FFs. And then all I have to do is take my SU over sigma prime I, and I get my SU over sigma prime I. And in this case, they're not as close, 0.5, 0.4. No matter, we'll just live with that. We write our UXS's here, 425 and 900. Those are our UXS's at failure, which means we can get the sigma prime at failure by simply the sigma prime I minus the UXS. So remember, sigma prime I is also equal to sigma. So because there's no UXS at the end of the consolidation phase. So our sigma prime FF is simply that sigma minus that UXS. And we get these values for our sigma prime FF. So we can then plot those. So we have our sigma prime FF, we have our tau FF. We plot them, X, Y, right there. our x, y right there, and our m, you can figure this out, delta y over delta x, there's my m. The arctangent of m is my phi prime, and then I create my expression, my y equals mx plus b. In this particular case, we're choosing this point here, so we put in the 1717 and the 1071 for that point, and we solve for, C prime. I get C prime is equal to 400 PSF. So I've been able to get both the phi prime and the C prime from these tests. All right, I'm going to stop there.